Good afternoon, everyone. I was very pleased to accept Professor João Figueiredo de Sousa's invitation to participate in this session of TrainMoS. I will be doing a series of lectures in the next few days regarding energy policy, energy and transport, with a particular focus in the European Union. My name is Guilherme Mata da Silva. I know that Fernandes already did some introduction. I would just like to say that I'm now working as a consultant in the transport sector, involved in national and international projects. Previously, I was a member of the board at the Portuguese Maritime Administration, and before that, I was a member of the cabinet of the State Secretary for Transport. Energy issues. I would like firstly to take a step back and just briefly go over a few concepts regarding energy and energy technologies, particularly relevant today. I will be describing the energy sector globally and not with a particular focus in the transport sector for now. Today's presentation is on energy trends. So to begin, energy is defined not very clearly, but as the ability of a system to perform work. In terms of physics, I am told this is actually a very complicated definition, but I'm going to trust this one because it seems simple enough. So it is an inherent property of matter which assumes several forms. You can assume the form of kinetic energy, chemical energy, potential energy, elastic energy. We're all familiar with several of these kinds of energies when you turn on the lights in our homes, when you turn on the engine in your car, and you take the bus to work or to school. These are all several forms of energy on which we've grown increasingly reliant. Energy has another property, which is it cannot be created or destroyed. It's inherent to matter and can be transferred to other objects or transformed from one form to another. So the chemical energy contained in oil, for instance, can be transformed into mechanical energy through an internal combustion engine, or to heat energy in a furnace, and subsequently transformed again and again. For instance, in power generation, you can take oil or gas or coal, burn it to heat water. Water will turn into steam, which is less dense than water. It occupies a larger space and moves a turbine, creating electricity. This electricity can then be changed again into motor energy or kinetic or thermal energy through other types of conversions. As I said, we've grown increasingly reliant in several forms of energy for modern life. It also allows us to change the environment around us and make conditions more habitable and more pleasant. For instance, negating cold during cold weather or creating cool air during warm weather. It allows us to perform tasks at night when that was previously impossible or difficult with just rudimentary forms of light, candles or other types of flames, open flames. It allows us to move much farther, faster, and with heavier loads than previously. It is used in industry, of course, to produce the myriads of goods that we consume every day, and it's used just about every minute of our waking lives, in our phones, in our computers, in our cars. Everywhere we are relying on energy to basically live life as we know it. Prior to the Industrial Revolution in the 18th century, energy was of course already used, and it was important to societies, not nearly as important as it is today. The primary uses of energy were for burning, for cooking and lighting. Sometimes they were used in industrial process or in transformative processes in the industrial, such as in windmills or water mills. Animals were used in agriculture to help cultivate crops. But even before the Industrial Revolution, the use of natural fuels such as wood for burning led to a decrease in the number of trees existent. And in the 18th century, you could already notice a shift to coal in Great Britain because of the scarcity of wood in some areas and the abundance of coal. The turning point of this process of increasing reliance on energy was the invention or the perfection of the steam engine by James Watt in 1781. There were, of course, previous models of steam engines. People had tried to harness the power of steam for a number of centuries before. But the technologies, the several components that came together to build a steam engine and really for the first time really harness the power of steam, that only happened with James Watt's steam engine. It had the advantage, but at the same time limitation, that it could be used wherever water was used to generate steam, and coal or wood existed to use as fuel. The steam engine revolutionized industry and transport, mainly in the 18th century. It allowed for extremely large machines that could perform the work of several tens or hundreds of people, and to build machines that were previously impossible to build. It was also applied to transport, notably in trains, the first day-to-day uses, but also in steamboats and other steam carriages were also experimented on. Also, the increased use of coal allowed people to develop other processes that were already using it as a fuel, namely in smelting, and it allowed for the production of higher quality steel, which in turn allowed for their use in new boilers, new engines, new machines, all harnessing this new form of energy. During the 19th century, there were several developments in terms, namely of energy sources that became used. In 1821, although people were already familiar with natural gas seeping from the ground in certain zones, in 1821, near New York in Fredonia, the first successful natural gas well was built. This gas well was used to supply a nearby town with gas for urban lighting. But the lack of infrastructure to transport gas, so pipelines or other forms of storage and transport, prevented their widespread use of gas during the 19th century. This infrastructure would only be developed in the second half of the 20th century, even though gas was used frequently for city lighting, but it was localized use. There was not much global trade in gas, and other sources competed with gas for the same uses, such as whale oil in city lighting, electricity, starting at the beginning of the 20th century. Today, gas is one of the major energy sources, especially in electricity generation. We now have advanced gas-fired combined cycle steam turbines, which are some of the main users of natural gas today. This is because coal was found to be extremely pollutant compared to gas, Also, the supply of oil was subject to major shifts in prices and subject to geopolitical factors. So there has been, especially in the EU, a shift from other fossil fuels to natural gas. I would like to add, in the meantime, the definition of fossil fuels are those that were created. So they are an energy source, they're a fuel. They were created in geological timescales. They are created from biological deposits that are compressed under the earth, underground, and develop over millions of years. And this is why they are called fossil. This in contrast to renewable fuels, which regenerate in a normal human time span. Continuing with the history of power sources, in the late 1800s, there were big steps forward in the field of electricity. There had been a number of scientists more or less seriously toying with electricity, sometimes not really taken seriously. But for instance, Volta was the first to build a battery, which is a stack of metallic components, which together with an electrolyte generate a current. Anyway, in the late 1800s, Nikola Tesla and Edison both concurrently made significant strides in the technology of electricity generation and distribution. In fact, they're often described as adversaries due to their different technologies. Nowadays, we use both. For instance, Tesla was a proponent of alternating current, if I'm not mistaken, while Edison proposed direct current for electricity distribution. They both had advantages and disadvantages, but in the end, alternating current was the winner for overall electricity distribution. After the 1960s, with the advent of digital technology, we increasingly started to transform alternating current back into direct current to be used in our digital devices, which are not compatible with the power cycles of alternating current. Also in the late 1800s, oil was started to be exploited very seriously for the first time. This was due to not only the development of drilling technologies, but also the discovery of major reservoirs of oil. Oil was a substitute for other fuels which had become widespread, such as whale oil in lighting. In fact, whale oil was the first fuel where we actually saw a phenomenon called peak whale oil. There was such a high amount of whale hunting that whales started to become extinct and fuel prices soared. And the industry started, the production started to level down until it was superseded by oil. The use of these combustible fuels, as oil and gas, also led to the invention of the internal combustion engine. We've spoken about the steam engine, where steam drives a turbine or a piston to make the engine move. This happens outside of so there's a separation between the fuel and the fluid that makes the motor, the engine move. They are therefore called external combustion engines. You have a fuel that is burned, and then you have the water vapor, which is heated and makes the engine move. These are separate processes. In the internal combustion engines, fuels are burned inside the engine and make the engine move in the same chamber. This spurred the appearance of the automobile with the impact that we see today. At the same time, the developments in electricity had also generated the discovery or invention of electric engines, but they were not nearly as efficient or long range. Energy storage has long been a problem with electricity. It's not easy to generate and then store electricity for later use at will. And therefore, very early in its life, the electric engine was replaced by the internal combustion engines for automobiles. Regarding nuclear power, which is one of the more recent sources, it came about based on a number of developments in physics, in particle physics. In the early 20th century, Einstein proposed that all matter was energy and it was interchangeable. So every particle, every atom in the universe contains a given amount of energy, which according to calculations was a very significant amount of energy, far superior to that contained, that can be released through other processes such as chemical process. Burning fuel is a chemical process. You oxidize the fuel and the reaction causes heat. But this energy is much lower than the total energy contained in the fuel. By 1938, the first demonstration of uranium atom fissioning had taken place. This happened more or less concurrently with the beginning of the Second World War. There were many physicists studying this subject in the United States, but mainly in Germany and Italy, and also in the Soviet Union. So it became, it was captured into the politics of the Second World War. In 1942, the first sustainable nuclear reactor was built near Chicago. It was called the Chicago Pile 1, under the direction of Italian physicist Enrico Fermi. Until the end of the Second World War, nuclear energy was, the research in nuclear energy was reserved chiefly for the search for an atomic bomb. The various potencies in conflict were researching this use for atomic energy. The United States, as we know, made the first atomic bombs and used them at the end of the Second World War in Hiroshima and Nagasaki. But once this conflict was over, researchers and politicians turned to the civilian applications of nuclear energy. And so in 1954 to 1957, a number of civilian, well, I wouldn't say civilian, but a number of nuclear reactors for civilian purposes were built, first in the USSR, then in the United Kingdom, and finally in the USA. These were nuclear reactors used in generating electricity, and no longer for harnessing the nuclear power in war effort. In terms of renewable energies, they have a long history, but have taken increased importance in recent years. Renewable energy, as I already mentioned earlier, is energy that comes from resources that are replenished within a normal human time span. So wind, solar, hydro, geothermal, and biomass. This may be less apparent in biomass, but if you consider that if you cut a tree to burn it, you can plant a new one and it will have the same size and energy content as the first one in a few decades, I think you will understand what I mean by replenished on a human time scale. These forms of energy were already used in some applications, namely wind and water. They were used for mills to move constant rotation, and that could be used subject to availability of wind and water. However, in the late 20th century, we have realized that we are increasingly reliant on exhaustible resources, which are not replenished in these timescales, but rather along millions of years, which is the case of fossil fuels. The theory of peak oil was theorized by several people until it was more formalized. But ever since the early 20th century, some people in the energy sector have theorized about peak oil and peak gas and the peak moments of other fossil fuels. The peak does not exactly mean that we've run out. Peak oil is a different concept from oil exhaustion. Once we reach peak, it means that the oil reserves we have and the cost of extracting them are no longer competitive compared to other sources, and therefore production winds down. It does not necessarily mean that we've run out of oil, but oil is harder to extract and not as competitive. Of course, it is a fact.
But if we face an increase in energy prices, maybe some part of that oil could be extracted.
Of course, and we see that today.
And we move forward.
Exactly. We see that today. I will speak about this a little further along, because certain unconventional oil resources have been exploited recently because of increased oil prices, which make them competitive when they were not previously. Other factors contributing to the increase in the use of renewable energy sources include supply security. Renewable sources are often endogenous resources, which means they exist at the location where they are used. Fossil fuels are mainly transported to other locations to be used. So a producing country may export them to another country which does not produce fuel, but requires it to maintain its standard of living and to maintain society as we know it today. Renewables, such as wind or water to a lesser extent, geothermal, they are available on location and can be harnessed even if you don't have fossil fuel deposits. This increases as I was saying, the use of endogenous sources increases the security of energy supply and therefore mitigates the risks that there will be a shortage of energy sources. Also increasingly important are the environmental concerns associated with the use of fossil fuels. Not only greenhouse gases, which is a major theme currently, there are no emissions, no greenhouse gas emissions at all from wind or solar, if you discount the production of the generation facilities, of course. But in generating power, there are no emissions in these technologies. Hydro is a mixed case because the creation of a new water basin, which is then used to generate hydropower, does have an impact on greenhouse gas emissions, and therefore large-scale hydro. Other than greenhouse gas emissions, fossil fuels also emit other types of pollutants, chiefly nitrous oxides and sulfur oxides, which contribute greatly to the degradation of air quality, to acid rain, to the reduction of biodiversity through the effects of this pollution and acid rain, and also to human diseases such as respiratory diseases from particle inhalation. Despite these advantages, renewable energy has some shortcomings. Sources are often localized, so you cannot generate wind power anywhere you wish. You have to have abundant energy resources available. The same with hydrological and geothermal resources, or solar power, which requires areas with particularly high solar incidence throughout the year. These are often infant technologies. They require high cost to development and deploy. The efficiency is still not at its theoretical peak, although there have been great improvements, namely in photovoltaic solar. But it's still extremely expensive to deploy large-scale renewable energies. In addition, renewable energy is not always available on demand. What I mean is, the wind is not always blowing and the sun is not always shining. And if you rely exclusively on these kinds of energy sources, you will risk not having them available when you need them for periods of higher need. At the same time, you might have excessive production at other times. During off-peak times, you will still have wind turbines running, and the sun will still be shining on solar photovoltaic panels, and therefore you can either waste that energy or you have to find solutions to store them. Now, as I mentioned, electricity storage is not easy. The density of energy storage is not very high, therefore you need very large batteries to store a significant amount of electricity. Also, the ability to then remove that energy on demand is sometimes limited. Sometimes you can't get it back quickly enough, or you don't have enough of it stored. Some solutions have been created to mitigate this issue. For instance, wind power is often used to pump water back into reservoirs in hydropower stations. Therefore, they are used in turbines to produce electricity, stored in another basin below the main reservoir, and then pumped back up via wind power to use excessive wind power generated in off-peak hours, because this energy would otherwise go to waste. I have here a graphic showing the evolution of energy use, and it's very apparent the increased reliance on energy in modern societies. As you see, up to the 18th century, energy use was fairly constant. It rose linearly, and it can be correlated with population growth. But after the Industrial Revolution, energy use grew exponentially. We have found more uses for energy, more sources of energy that we are harnessing, and this has allowed us to rely on energy to build modern day society. And in fact, there is a strong correlation between energy use and gross domestic product in most nations, although that reliance has been declining slowly. As you see here, this is the population growth, which is in blue, the blue line. It no longer follows the red line, which is energy use. After this introduction, I will now present a few facts on the current situation regarding the energy sector. In global terms, in 2012, demand was over 13,000 megatons of oil equivalent. This is from the several available fuel sources, coal taking the largest share at nearly 30%. Oil at around 30%, 31%, followed by coal at 29%, gas 21%, and others at around 20%, including renewables and nuclear. As you see, nuclear is fairly residual. It is disputed whether this situation will change in the near future. As I was saying, there's a very strong correlation between energy consumption and economic well-being and economic growth. This is called the energy intensity of economies. This has been decreasing, but is still a very significant factor and contributes to make energy issues central issues in policy and even in geopolitics. Recently, we've seen steep increases in oil and gas prices, as Andrei was mentioning earlier. This has made it possible to exploit unconventional sources of oil and gas, such as shale oil and gas and tar sand. These resources were in many cases already known, but access to them or the degree to which they have to be refined in order to make them usable was not economically feasible. The increased oil prices now make them competitive vis-a-vis other oil sources or other fossil fuel sources. At the same time, the uncertainty of supply is also a main factor driving energy policy today. As we know, many oil-producing countries are subject to political stresses, sometimes situations of war, which may disrupt production. And therefore, most nations have sought to diversify their fuel mix in their economy to obviate or mitigate these concerns. Also, as I mentioned previously, the current energy mix raises a number of significant environmental concerns, chiefly the greenhouse gas emissions. Fossil fuels, when burned, emit CO2 and other gases which heat up the atmosphere and contribute to global warming. Other pollutants I've already mentioned, nitrous oxides, sulfur oxides contribute to acid rain and respiratory problems. It is estimated that there are around 600,000 premature deaths each year due to respiratory problems attributed to emissions, to gas emissions, although not solely from fossil fuels. In terms of trends for the future, I am basing these data chiefly on the International Energy Agency's World Energy Outlook 2014, which is the most recent one. The edition for 2015 should be out in the next couple of months. This is a very significant study of the current situation and future trends of the energy sector. The International Energy Agency has made their projections up to 2040 under 3 different scenarios. There is a current policy scenario, which is a business as usual scenario, typical in these kinds of studies. There's a new policy scenario, which is the central scenario, which is it is the one they consider most likely to take place. Scenario. The 450 scenario basically corresponds to a scenario where nations in the world met the International Panel on Climate Change recommendations to achieve only a 2-degree increase in global temperatures, and that implies limiting CO2 in the atmosphere to 450 parts per million. So these are the three scenarios. This 450 scenario is not considered very likely to take place. So we will focus our analysis essentially on the new policies scenario. According to the IEA, energy demand should increase up to 37% by 2000, and should increase up to 37% by 2040. This is spurred mainly by growing economies. OECD economies will see their energy uses grow, but not so quickly as in China or India and the rest of it. Especially in developed economies, the growth in energy demand is slowed by efficiency gains. But as we've seen, overall, the demand will still increase close to 40%. Asia becomes the largest energy consumer, and by implication, it becomes the largest buyer of energy products. So the market will start to shift from the United States and Europe towards the east, towards Asia. On average, the greenhouse gas emissions will largely overshoot the objectives for the IPCC's recommendation of 450 parts per million, which would allow for a 2-degree increase in average global temperatures. In terms of sectors, most of the demand will be for the power sector. Many economies are still not very electrified, meaning that not all people have access to electricity, especially in sub-Saharan Africa. There will be, therefore, a very large increase of energy demand in the power sector. Also, less developed economies will see their industrial sectors grow significantly, and that will also require investments in the power sector in order to meet demand. In terms of the final use, most of the demand will be to meet the industrial sector, transport, and buildings. Vehicles, for instance, are expected to double between 2012 and 2040. The electrification of societies that currently don't have access to electricity will also have an impact in terms of current uses for heating, for illumination, etc. Transport will see a growth, but not as significant as one might expect from a doubling of existing vehicles. This is because there are already in place several policies and measures aimed at increasing fuel efficiency in the transport sector. Fuel efficiency and to reduce emissions. And therefore, although there will be more vehicles and there will be greater needs for fuel, the same fuel will go a longer way in the same fuel. And therefore, the growth will not be as strong. We can see here the International Energy Agency's estimates up to 2040. We can see that under the current policy scenario, which is the business as usual scenario, we would see a significant increase in energy demand. This increase would be a little smaller in the new policy scenario, but still fairly high. We would go from around 11,000 megatons oil equivalent in 2014 to over 18,000 megatons oil equivalent. In the hypothetical scenario where we would meet the IPCC's 450 parts per million goal in greenhouse gas concentration in the atmosphere, we could only emit a little below 16,000 megatons oil equivalent. So there is a fairly wide gap between that and what the IEA estimates will actually occur. In terms of the relative share of the several energy sources, fossil fuels will lose importance, but not by much. They currently represent about 80%, a little over 80% of the global energy mix. It should fall to around 75% of that energy mix in 2014. An interesting fact is that fossil fuels as a whole will represent 75%, but each type of fossil fuel, roughly grouped into coal, oil, and gas, will take up equal shares of around 25%. This is explained by a shift to natural gas due to the recent availability of conventional sources and the feasibility of some production operations due to increased oil prices, and also to the lower carbon content of natural gas, which will make it displace oil and coal in sectors where fuel replacement is more feasible. In the transport sector, for instance, it's harder to displace oil because the efficiency and range of natural gas is still not on par with gasoline, diesel, and other oil-derived fuels. So we will see from the graphic I showed you in the beginning, the current situation. Oil had 31% share in the global mix. It will come down to around 25%. Coal will also come down from 29%. Gas will go up, driven mostly by the shift in fuels from higher carbon fuels, higher carbon content fuels, to lower carbon content fuels such as natural gas. Still, oil will still be the single largest energy source in the global energy mix. We can see here the graph I showed you before, next to the estimates for 2014. As you see, oil remains the largest contributor to the energy mix, 26%. Natural gas and coal are tied at 24%. And other energy sources are roughly tied to each of the fossil energies, fossil fuels at 26% combined. Nuclear is estimated by the IEA to grow from 5 to 7% of the global energy mix. I would say that the uncertainties regarding nuclear are particularly high. Because nuclear is not only dependent on physical aspects such as the extraction of nuclear fuel and the construction of new capacity, but also political and strategic issues. Nuclear is a very sensitive issue due to a number of factors, including the safety of operation and disposal of nuclear fuel. But we will go more into each of these energy sources a little bit later. Renewables will grow 5%, which seems low, but in fact this represents a very large increase in the power generation sector. A smaller increase in other sectors where renewables are not as economically feasible, such as in transport or industry. Um, in terms of each energy source, for oil, the IEA estimates that demand will rise from 90 to 104 million barrels a day by 2014. And oil prices are expected to rise to up to $132 per barrel. The increased efficiency and fuel switching that I mentioned earlier should restrict the growth of oil use. And in fact, we've seen that oil is displaced in the global mix by other fuels, while remaining the main fuel of the global mix. It loses share to other energy sources. In the fields of transport and petrochemical, where it's not as easy or even technically possible to find a substitute, oil will remain central for it. The growth in oil consumption will likely restrict itself to non-OECD countries. Why? Because in OECD countries, natural gas is largely taking the place of oil in energy generation. And as we've seen, the increase in vehicles should be met by increases in fuel efficiency, which will require less oil to operate the same or even higher number. At the same time, there are policies and measures in place to use natural gas also in the transport sector and to use hybrid or full electric vehicles, which would also contribute to reduce oil. For each barrel that is not consumed in OECD countries, as I was saying, it is estimated that each barrel that is not consumed in OECD countries is equivalent to 2 barrels that are now used in non-OECD countries due to the development of these economies. In terms of producing countries, we've seen recently an increase in the importance of the United States and Canada, for instance, in oil production, namely from non-conventional sources. Canada has been exploring tar sands, and the US has been mostly exploring shale gas and shale oil. However, the OPEC countries should still represent the majority of oil production by 2040. A consequence of the shifts in the energy markets in 2040 will be felt particularly in the refining sector. Right now, the greatest consumers of oil are the US and Europe. By 2040, the focus will have shifted to Asia and mainly China and India. Therefore, the excessive refining capacity that some people already identify today in Europe will become a larger problem as the consumption shifts towards Asia. And industry will either have to relocate or to deal with these new centers of oil trade. You can see here a graphic of estimated oil demand and prices. In the main scenario, which is the new policy scenario, I'm sorry, I believe I didn't really explain the new policy scenario. I only explained that there's the central scenario in the IEA projections. But the new policy scenario is the one where countries continue to adopt certain policies to increase fuel efficiency, to reduce reliance on fuel imports, and therefore tackle supply security, although not to the extent required to meet the goals of the 450 part per million CO2 scenario. As we see, oil demands are quite a bit higher than what would be necessary to meet the greenhouse gas emissions for 50 scenario. In terms of prices, you can see that prices will continue to increase. They were very low in the last few years of the 20th century, then saw a sharp increase, which is where we saw a shift towards more non-conventional oil sources, and prices will continue to rise up to 2000. In terms of sectors, we see that oil will actually, although it will increase in total volume, it will decrease, for instance, in the power generation sector, an average of minus 3.1% per year until 2040. This is because oil will be replaced by other lower carbon intensive sources in power generation. It will grow in transport, although at a rather low rate of 0.8% year on year, due to the increases in fuel efficiency and the substitution of other fuels. In petrochemicals, the consumption of oil will see the largest increase, 1.5% year on year on average. And other industry will see oil grow at a reduced rate of 0.1%. Buildings, we're talking mainly about heating the oil, because electricity is already covered in the power generation sector. So oil for heating will also see a reduction during this period. With regard to natural gas, the use of natural gas is expected to grow very strongly up to 2040. As we've seen the share of natural gas should grow from 20% today to around 25% in 2040, which, coupled with increased demand in total energy, represents a significant amount of new natural gas that will be consumed. It's estimated that by 2040 we will be consuming 5.4 teracubic meters of natural gas. It is very close to oil as the main source in the global energy mix at the end of the projection period. Whether this increase happens and to what extent is contingent on governmental policies regarding the construction of capacity for the transport and storage of oil, and also for the exploration of new oil reserves. These have been tied to some regulatory hurdles, namely due to the unknown environmental impacts of some extraction technologies such as hydraulic fracturing or fracking. The transport sector is the sector where natural gas use is expected to grow the fastest. In terms of geographic distribution, the growth will be focused especially in China and the Middle East, but also in the US, in this case because of the existence of local natural gas reserves. The production of natural gas is expected to grow globally, except for Europe, which doesn't have access to large natural gas reserves, and this may lead to increasing difficulties in ensuring supply security. We've seen recently with the conflict between Russia and the Ukraine that the energy issue was central to that conflict. Europe is supplied in large part by pipelines coming through the Ukraine from Russia. And this susceptibility of natural gas to political disturbances, if not adequately addressed, may either jeopardize the security of supply or dictate an increased use of other fuel sources. So oil may not, natural gas might not take such a significant position in the global energy mix. To address this issue, countries are pushing for the diversification of their sources of natural gas. New pipelines are being built and are expected to be built during the next few decades. Also, liquefied natural gas shipping will take on a fundamental role in ensuring the diversity of natural gas sources, so that countries are not excessively reliant on one supplier. In terms of global demand for natural gas, once again we see a sharp increase in demand between 2014 and 2040. This is significantly higher than that which we would be allowed to have in order to meet the greenhouse gas emissions budget of 450 parts per million, and somewhat lower than a business as usual scenario due to the new policies that are expected to be implemented. Sorry. In terms of distribution by sectors, we see that the power sector is the largest, or is expected to remain the largest consumer of natural gas. It now consumes 1,400 billion cubic meters of natural gas today, and is expected to increase consumption to 2,100 billion cubic meters of natural gas. This sector is closely followed by industry, which is expected to consume 1,300 billion cubic meters of natural gas. Buildings, displacing oil, transport, and then other energy sector industry. Switching to coal, most of the increase in coal use will come from China and later India. China already has a very substantial installed capacity of coal-fired energy generation plants and is expected to build more over the coming years to the detriment of air quality and greenhouse gas emission targets. Elsewhere, coal is expected to lose some of its importance for the same reasons of environmental concerns and the existence of alternative lower carbon fossil fuels. However, the continued reliance on coal may have slightly lower impacts if we are able to use higher efficiency technologies in coal-fired plants, sometimes dubbed clean coal, and through the use of carbon capture and storage, or CCS, to mitigate emissions. CCS are systems, carbon capture and storage are systems that recover the emissions from burning fossil fuels and store them typically underground. One of the technologies proposed for this is to pump exhaust emissions from burning fossil fuels in power generation into oil and natural gas wells in order to displace the gas and the oil, allowing for their extraction, and in turn to store the CO2 underground for long periods of time. However, I should say that there are still great uncertainty on the feasibility and cost of these carbon capture and storage technologies, and that there are no commercial systems operating as of now. We have here the changes in coal demand, production, and trade. In each of the scenarios, I would like to focus on the new policies, which is the most likely scenario. So as we see in the OECD, we actually see a decrease in demand for coal and an increase of production. Whereas in non-OECD countries, there is also an increase in production, but this is accompanied by a significant increase in the demand for coal. In terms of nuclear, in 2013, there were 392 gigawatts of installed capacity. That represents 11% of total electricity generation, which is a decrease from previous years. The nuclear as a fuel in energy generation peaked around 1996 at circa 18% of total electricity generation and has been winding down since then. Most of the capacity, 4/5 of the installed capacity of nuclear nowadays is in OECD countries. However, this also has the effect that much of this capacity, being over 25 years old, it is expected to be decommissioned or to be retired in the coming years, which leads to a new problem, which is whether and how to build new nuclear capacity. This is a hot issue in almost everywhere in the world. There are serious concerns on the security of nuclear facilities and also the safe disposal of nuclear waste. We recently had an example of an industrial accident involving a nuclear facility in Fukushima. And the insecurity felt by populations is a major driver in the political process that has to take place in order to allow for the installation of new capacity. In terms of the disposal of nuclear waste, although countries with nuclear facilities have an obligation to deal with this sort of waste, as of now, there are no definitive solutions anywhere for the storage, for the permanent storage of nuclear waste. All of the storage technologies that currently exist, the storage solutions, are considered temporary. As I was saying, there is a very high regulatory uncertainty, which makes investment very high risk and often non-financeable, because it's impossible to find financing for projects when you don't know what the regulatory framework will be. As I said, there are still a number of gray areas regarding nuclear power that need to be regulated, and we still don't know if and when regulations will be enacted. That said, there are many countries poised to phase down their nuclear programs, but also to introduce new nuclear programs or continue existing nuclear programs for power generation. Here we see a graph of the construction of nuclear reactors. The yellow bars represent constructions in OECD countries, and as you can see, it represents vast majority of existing capacity. So in yellow we have the build capacity in OECD countries, and we can see a shift towards non-OECD countries represented by the yellow bars in recent years. In terms of total share in electricity generation, as I said, it peaked around the late 90s and has been phasing down. This is the global average. It peaked at around 16% and winding down. It's now close to 10% global makeup of the energy mix. Despite what I've said about concerns involving nuclear power, it is expected that installed capacity will grow by about 60% until 2040. Again, we're talking about projections, so this will be dependent on a number of assumptions made in the study, but the International Energy Agency concludes that by 2040 there should be 624 gigawatts of installed capacity in nuclear, up from 392. As you see here, most of this installed capacity will be located, most of the new capacity will be located in non-OECD countries, with only a fraction being located in OECD countries. The decrease in the full areas that you see here represents the decommissioning of existing plants, which will not be completely replaced during the period covered by the study. Going to renewables, the use of renewables is expected to grow very strongly, up to 19% of the total primary energy mix by 2040. This increase will be driven mostly by the power generation sector, and in this sector, wind will represent the largest amount of increased capacity of renewables. The expected installed capacity of wind power in 2040 is 1,220 gigawatts. Solar photovoltaic will also expectedly see a very large growth, up to 930 gigawatts of installed capacity. In the renewable sector, subsidies are expected to continue to play a very large role. As I mentioned earlier, the use of alternative fuels and food sources still requires a very large investment. There's still a lot of research and development being done in order to increase efficiency of generation systems based on renewables and the production of generation facilities. In 2013, around $120 billion were granted in subsidies to the renewables industry, and this is expected to increase to over $200 billion by 2030. At that time, the first facilities which benefited from public subsidies should be decommissioned by then, and total subsidies should then start to decrease. We see here an estimate of the share of renewables by sector. In terms of total primary energy demand, the green bar over here are the high and low ends of the estimates of the study, and the low end represents the 450 scenario, the high end represents the 450 scenario, and the low end represents what will be achieved with no changes in current policies. As we see, the increase of renewables will be most important in the electricity generation sector, but in heat and road transport, there will also be very visible, very noticeable increases. In terms of greenhouse gas emissions tied to the energy sectors, the International Energy Agency's main scenario predicts that the IPCC's proposed budget to limit global warming to 2% to 2 degrees above current above 1900 levels will not be met. We can see that
questa connessione qua mi sembra più lenta, però no?
As I was saying, the IEA predicts that greenhouse gas emissions will continue to grow up to 2040 above the budget allowed for in the IPCC's recommendations that would allow for global warming of 2 degrees Celsius. Reach a concentration of by 2100 should reach 700 parts per million concentration of CO2 equivalent in the atmosphere, and the estimated impact in global temperatures is 3.6 degrees rather than the 2 degrees proposed by the IPCC. A few countries and areas will reduce their annual emissions by 2040. However, in reducing those emissions, they will still remain the largest single emitters because they have a very they are now much higher emitters than other countries. So the USA, the European Union, and China, although they are expected to reduce total emissions, they will still be far above other countries and regions. As you can see here, the US, the emissions in the period 2013 to 2030 in this light orange line area will decrease to in the period 2031 to 2040. However, the total emissions of the United States will still be significantly higher than India, the Middle East, Japan, and the rest of the world. We can also see here that the per capita emissions will still be there will still be very large discrepancies in per capita emissions in different areas. So the United States will be by far the largest emitter per capita, followed by the Middle East, Japan. The European Union, as we see, is kind of middle of the table. And India, despite having a significant increase in emissions, will have a per capita number of emissions, which is much lower than that of other areas. This is actually all that I had prepared for this topic. I'm sorry, I seem to have rushed a bit. We're still into the first period that we had foreseen, but this is the material that I have for you for now. I don't know if you have any questions that you would like to ask. I'm sorry if my too complex in certain technical issues. I will be posting some materials in addition to the PowerPoint, if that is allowed by the. I have discussed this, but I will include this presentation and other reference materials. And if there are no questions, I will see you all tomorrow at 9 for the next lecture. Thank you all.